Hello and welcome. Welcome to the first lecture on financial mathematics for actuaries. In today's lecture, we are aiming to set the brief context of this course, try to design the mechanics on which this course will be based. Mechanics, as you can see in the slide, is measurement of interest. Okay, so before coming to measurement of interest, let us understand how important is financial mathematics in our day-to-day life. Every one of you who is listening to this recording must be either in the role of a saver, investor, or a borrower, or you might be having some insurance policy or a pension plan or some saving account. That means you are actually handling a financial instrument in your day-to-day life. When it comes to financial instruments, there are a variety of financial instruments that are available, and in these variety of financial instruments, private organizations, commercial organizations where they deal with finance, government bodies, all are involved in these financial instruments in some or other manner, and therefore it is inevitable for us to study finance or financial instruments. When it comes to finance or financial instruments, it is important to understand how these financial instruments help us in building our financial future, and that is where significant number of numerical calculations and other kind of stuff comes in. When we speak in plain language about the financial instruments, it is very difficult to understand because of the confusion that pre-exists in our verbal communication. Therefore, it is inevitable to study financial instruments through mathematics, and that is where our course on financial mathematics builds the foundation. Okay. Now that we have established that every finance deals with money, and in order to understand the money transactions or financial transaction better, we need to have some understanding of financial mathematics. Let us dive into our roadmap for today's lecture. So, when we are dealing with money, how to handle money is a major concern, and that is where our first agenda in our today's roadmap becomes important. We will understand money through time preference. So, we will establish the axiom of time preference for handling money, and that is where it will help us in understanding the financial instruments. Our next agenda is to define the accumulation function, how the money that we are accumulating is accumulating at what rate. We will define a mathematically precise terminology for that, which is known as accumulation function. Next, we will consider a function which is called amount function or cumulative accumulated amount, which is defined as AT, and we will establish the fundamental relationship between the accumulation function and the cumulative accumulation of money. And then finally, we will distinguish between how the money is accumulated, or we will distinguish between two different methods of accumulation. One is linear, another one is exponential. These contents that we are discussing are referenced from Brouwerman's book on mathematics of interest and credit. You can have a look at section 1.1 of that book, and Chan and Say Financial Mathematics for Actuaries, sections 1.1 and 1.2. These are the reference readings that are required to understand these contents in a more elaborate manner. So, let us begin with the first agenda of this particular lecture. We want to establish the axiom of time preference. For that, I will ask you one basic question. If I offer you rupees 100 today or 1 year later, which one will you prefer? Would you prefer to take 100 rupees today, or will you prefer to take 100 rupees 1 year later? Okay. So the natural answer will be, if somebody is giving money, why should I refuse? I will take it today, right? So is that a rational answer? That's what we need to figure out. And if so, why it is a rational answer? And that is where we will establish our axiom of time preference. For example, if I take these 100 rupees today and if I invest it in some bank, or if I keep it in some bank, 1 year later, the question is, what will be the value of that money? So your bank may be offering you 1 or 2% interest rate or 5% interest rate, depending on the choice you depending on the bank you choose, your interest rate may differ, or depending on the scheme you choose, your interest rate may differ. In such cases, what you are actually saying is 100 rupees today is not 100 rupees 1 year later. What does it mean? Say for example, if I take 100 rupees from you today and I invest it in a bank at 5% rate of interest per annum, then I am actually having 105 rupees 1 year later, isn't it? So the rational answer is, I will choose it today. So the fact that we have established just now is called earning power of the money. The money that you have has earning power on its own, provided you invest in appropriate financial instruments. That means 100 rupees invested today will become 100 plus interest. Okay. So this brings us to two questions. First question is, if I take 100 rupees today or if I take 100 rupees later, suppose somebody is interested in taking 100 rupees later, do I need to invest 100 rupees today for giving him 100 rupees later? No, I definitely need to take some amount which is less than 100, which will become 100 1 year later. Therefore, the initial value will be smaller than 100 rupees. This is the fundamental choice that establishes the fact that your money is just not the number that you are seeing. It has something called time dimension. For example, I will give you one more example to make this concept concrete. If you would have bought tea, the regular tea that you are taking today, how much it costed 10 years ago? So it must be 5 rupees or something. Today it is costing you 10 rupees, right? The tea that is served is same, but the value or your purchasing power has decreased with that value, right? So this is something that we need to worry about in finance, and that is where we are worried about money and the time dimension of money. Therefore, always remember, money has a time dimension. Let us make this concept more concrete. Basically, what I am saying when I say money has time dimension, 100 rupees today will not be 100 rupees next year, right? And we have already established the fact. So essentially, if you are considering, if I had 100 rupees 10 years ago, or I have some capital 10 years ago, same capital will work 10 years later. That is a wrong assumption. It is like saying you are adding 5 inches to 5 centimeters. Their units are different. So whenever you are trying to compare money, the rule that we must follow for any money transactions. So money transactions are essentially called cash flows in finance. So we must always move cash flows to the same point in time before comparing or adding them. For example, if you are comparing the transactions which are year ago and you are comparing transactions which are a year ahead, then you cannot compare them. you first need to bring them to the present value. That is where the notion of present value, which we will study in future lectures, will become very important. And therefore, whenever you are comparing, you either go to that time point and evaluate your money for that time point. One benchmark is interest that we just discussed, but this particular principle, that value of money varies with time, can be named as time value of money, or you are essentially saying that money has a time dimension. Now that we have established the fact that money has time dimension, it is very important for us to navigate this dimension in an unambiguous manner. In order to do that, we will now introduce few notations which will help us to assess this time dimension. So the toolkit is now the notation. The first toolkit that we will design is the amount function. Typically, what you will look at is, if you have k units to invest as initial investment at time point 0, and you have invested that amount in some financial instrument, and the time has elapsed, say t, the time t or t in terms of years has elapsed, then what is your value of that invested amount at time point t? So that amount is called AT. Okay. So what we have done is, whatever money we invested at time 0, we called it as K, and that K is our principal amount. Then we have an amount function which essentially denotes the value of your investment at time point t, and then I need to define this accumulated value of principal K at time point t. I will call that function as amount function. Here there may be different currencies. You maintain one currency at given time point, otherwise it will lead to unnecessary complications. Okay, so now we have established what is called amount function. Now this amount function comes with different principal values K. I don't want different principal values. I want something that will set this K as a unit. So I will set it to 1, and that gives rise to our next function, which is called accumulation function. So I have set the K to be equal to 1 now, and whatever is the growth for this 1 unit, I will call that as AT, which is called accumulation function. So this also can be regarded as the rate at which my capital is increasing, 1 unit is increasing. So the definition is the accumulated value at time t of the amount of unit 1 that is invested at time 0. So here we don't fall prey to the units, rupees or dollars. This is simply the interest or the growth that we are getting. It's just a multiplier. So whatever principal you use, or whatever units of principal you use, you just multiply this multiplier, you will get the answer. Okay, so this is 80. Now the interesting question here is how to analyze this 80, because this 80 will determine your fate, whether your money will increase or decrease. That is the key question that we are going to address now. Before analyzing the behavior of 80, let us understand the connection between capital AT and small at, the amount function and accumulation function. So if you look at small at tells me how the unit 1 or 1 unit of my investment grows. If I have k units of my investment, then they will grow to k times AT. Therefore, The connection between capital AT and small at is given by this scaling equation, which is AT equal to K times small at. Here I have made a key assumption, which is linearity, that if I invest more, still it will grow at the same rate. That means investing 200 gives me 2 times investing 100. Okay. Generally, there are in market there are situations where if you invest more, you will get larger rate of interest. We will handle them later, but right now we are assuming the linearity principle, and we are assuming that if the way 1 unit grows, n units will, k units will also grow at the same rate. That's the basic assumption that we will deal with. Okay. So now that we have understood the scaling equation, which is AT is equal to K times small at, we need to understand how this AT functions, small at, which is the accumulation function. And for that, let us dive into the next slide. Here we are trying to understand how this small at behaves. So when I start initially at time equal to 0, what will be the value of accumulation function A0? When we studied, we defined 1 unit of time, 1 unit grows to AT at time t. But if there is no time elapsed, what will be the value of it? It should be 1 unit by definition, right? Because no interest is earned, and therefore 1 unit will still remain 1 unit. That's the idea, and that is how your growth function will happen. Growth function will behave. So now we have explicitly understood the boundary condition, which is initial condition also, you can say A0 is going to be equal to 1 and small at is the accumulation of 1 unit over time t. We are ready to dive into our next slide, which is how we can define the interest earned. Let us say we have one period and we call that period as period n. How we will assess the interest earned in that period? So that essentially means, what is an interest? Interest is the change in the accumulated value over a specific period. And now once we have understanding of capital AN, so if I am looking at nth period, what will be the accumulated value at that period? It is going to be capital AN. And what will be the accumulated value at one period before, which is n minus 1th period? It will be AN minus 1. So naturally, if I denote IN as the interest that is earned during nth period, this IN can be mathematically written as a formula AN minus 1, where, as I mentioned earlier, AN is the accumulated value at period n, and AN minus 1 is the accumulated value at period n minus 1. Then IN actually denotes the interest earned during nth period. Now that we have clear-cut understanding of what is IN, I will reveal one more trap. This IN is actually the value and not the interest rate. So it's an amount and it's not the interest rate. So don't confuse it with interest rate I. So next we will explore our growth models or the functioning of accumulation function. So the first growth model or the first modus operandi of accumulation function that we will study is simple interest. What is simple interest? It relies on the concept that interest is calculated only on the original principal. Okay. So let us understand it through some examples. So I will say that I have invested a principal of 100 rupees in a bank. At time t equal to 0, this 100 rupees are there. Bank offers me interest of 5%. So I am denoting R as 5%, which also can be written as 0.05. Okay. So under these two assumptions, how will the assumption of simple interest operates? So at t equal to 0, this 100 will remain 100. Let us assume at t equal to 1, what happens? So at t equal to 1, since bank is giving me a 5% interest rate, I will earn 100 into R, which is equal to 100 multiplied by 0.05%, which is 0.05 or 5%, which will give me 5. Okay. This is the interest accrued. I will add this to my original amount 100 and I will have a total capital of 105. But according to this principle, the interest will be only calculated on the original principal. So now if I go further at t equal to 2, which is time point of 2 years, how will I calculate the interest? So I have 100 rupees and I have invested it for 2 years. So what I will do is I will take this rate of interest R, I will multiply it with the time that I have spent and I will multiply that with my capital. And that is where what will happen is I will have 100 into 0.05 into 2, which will give me 100 into 0.1 and that will give me 10. Okay, and together this capital vehicle will become 100 plus 10, which is equal to 110. Okay, so now I can see the operation of AT here. So how will I write this AT here? So what is happening, if I have say t is equal to n, what will happen? The interest accrued will become 100 into R into the time that I have spent, so n, correct? And then I can easily compute the answer. And when I am computing this, what I am essentially doing, I am essentially taking this amount 100, I am multiplying it 1 plus R times n. Okay. So if I look at AT, this AT that I am talking about, small AT, which I am talking about, can be seen as AT is equal to 1 plus R times T. Okay. So in our standard notation, we denote this rate of interest by I. So your R is equal to I, and therefore the accumulation function that I will define in case of simple interest model is 1 plus I times T. That is what will be given on the next slide. 1 plus IT. So here we are actually assuming that the growth of this function is constant per period and the graph starts at line t is equal to 0 with initial 1 unit. Okay, so this I will show in the final slide, but right now this model is prevalent. We have proved this model. Okay, and it is essentially nothing but linear growth. Okay, now let us explore another mechanics of AT, which is called compound interest model. And now in this case, what we will do is interest is calculated on the accumulated balance at the end of each period. So let us start with our example, which is 100 rupees at time t equal to 0, and now at time t equal to 1, if the bank still gives me 5% interest rate at time t equal to 1, I will not see any difference because it will be 105 rupees, right? Because I will accrue an interest of 5% and I will add that to the amount. The difference comes when t equal to 2. At t equal to 1, I have 105. Now, the interest will be calculated on the accumulated balance. That means the next interest that will be calculated on 105. That means I will take 105 and I will multiply it with my interest rate I, which is 5%, and I will calculate the interest. Okay, so if I do that, what I will get? I will get the new amount, which is 105 into 5 by 100, which is equal to, so the new amount is 5.25, and then when I am trying to compute this, it is getting it is getting added to 105, so it will give me 110.25. So as you can clearly distinguish, it is higher than the one that we operated when simple interest model was there. How will we convert this into mathematical formula? Let us compare this t is equal to n years. What I am actually doing, every time I am saying, I am taking this as a principal and I am calculating interest on it and adding it back to that principal, right? So when I started first 100, I operated like 1 plus I. Okay. This is for t equal to 1. For t equal to 2, what I did, I took 100 into 1 plus I and I added another 1 plus I, or I multiplied by another 1 plus I. And for this is for t equal to 2. So what will I naturally do for t is equal to n? I will take 100, and what will be the amount that I have accumulated in n minus 1th period? It will be 1 plus I raised to n minus 1, and to this amount I will multiply by 1 plus I. Therefore, the formula that I get is 100 into 1 plus I raised to n. Hence, my accumulated value will be given by this particular function. So, my amount function will give me this. Now, when I talk about the accumulation function, I will reduce this to 100 to 1 unit. Therefore, my AT, if I want to talk about, it will be 1 plus I, the whole thing raised to t. Okay. So, that is what will come in the next slide, which is this. Because we are earning interest on interest, the curve gets steeper over time and you will get an exponential growth, which is given by 1 plus I raised to t. A final thing that we will see is the graph of these two functions together, and that will be given here. So you can easily distinguish, if I start with 1 unit and continue earning a simple interest, I will go along this blue line, is simple, and this gap will widen as you move forward in time, right? So this is where we establish the dominance of compound interest over simple interest, and these are the key principles that will help us determine how to take interest. In the next class as well, we will focus on these concepts and identify the trap when t is between 0 and 1. After identifying the trap when t is between 0 and 1, one should also observe that this gap is widening, and therefore as time goes to infinity, this divergence will be much bigger, right? So this concludes our first lecture, and let us summarize our findings. The first finding is there is a time value to money. That means money has a time dimension. You can never compare money at two different time points without bringing it to the same time point. Then, in order to understand this time dimension, we need the scaling equation, which is AT is equal to K times AT, where capital AT is amount function and small at is the accumulation function, where the number of units is reduced to 1. Next, we established the boundary condition, which is A0 is equal to 1 for accumulation function, and the interest IN, which will be given as the amount that is earned in the nth period on the accumulated value. And then in lecture 2, we will dive deeper into the math of simple and compound interest. Why does simple interest usually pay less, and when does it surprisingly pay more? Thank you for your attention.